And now I would like to invite for our second talk Andreas Knüpfer with a presentation titled Datalad Reproducibility for High-Performance Computing, the Datalad Slurm extension. Andreas Knüpfer works at the Center for Advanced Systems Understanding, CASUS, in Görlitz, which is part of Helmholtz-Zentrum Dresden-Rosendorf. He's the head of the Scientific Computing Core Department, the Computational Science Research and Support Group at CASUS. His background is in high-performance computing with methodology research as well as contributions to many application science projects from diverse fields of science. He also knows the perspective of scientific HPC centers and operating large clusters from one of the larger Tier 2 university HPC centers in Germany. His research-focused topics are parallel performance and scalability, as well as software tools for performance analysis, parallel programming models, and research data management. The scene is yours. We're looking forward to hearing the talk.
Good morning. Thank you very much. I would like you to bring a little bit the perspective of high-performance computing and how I think this really cool, really nice tools, GitNX and Datalad, how they should be combined with what's the common and usual thing in high-performance computing. Short outline, which I'm not going to read to you, of course. And then a little bit more background about the fairly young institute that was mentioned a minute ago, the CASUS Institute. It's all the way in the east of Germany, right at the border to Poland. A pretty young institute with a really diverse set of research topics from all the way from biology to astronomy. And then part of my team, part of the mission of my team is really to support with the computational science tools, so to make their research better, cooler, faster, bigger, you know. And then, of course, this research data management is an important part and is a challenge for some, and then we can help them. Now, the starting point here, where I'm happy that I don't need to explain all the details. Yeah, I guess some of you may have heard about it. Usually this takes many minutes to explain, but the machine-actionable reproducibility with this nice JSON record in your Git log, which makes it clear this is the computing steps that you need to do to reproduce some computation. This is really nice and it works, and I like it a lot, but unfortunately it clashes a little bit with the usual type or workflow on those big clusters. And this may be your institute cluster, or this might be the biggest cluster on the planet. And maybe a little bit of background how it works, because not everyone here will be familiar with it. So you don't like SSH into this big cluster and say, start my highly parallel thing, because this would not work for all sorts of reasons, but instead you need to talk to so-called job scheduler. Slurm is the one which is really used on most of the really big clusters. There are a few others with the same principle, how they work though. So it's like a job script, what you see on the left-hand side, what you need to give to it. And then you say, whenever you have the resources for me, so this is exclusive CPU cores or compute servers, or really many of them, and GPUs in the memory, whenever you have those resources for me, start my job there, exclusively bare metal, nothing else in between, and no other users at the same time. So that's why this is basically a shell script, but here those special comments. This is the definition of the resources you request, including the runtime. Run me for 3 days, for example. And then you can load some software modules, you can have environment variables, you can have a short preparation script, and then something like this is the parallel job, where you say, no, run on 10,000 CPU cores or whatnot. So you hand this over, and then this Slurm scheduler will run it for you on the weekend while you're on vacation, whatever. And you come back and you're happy when your results are in. And then one more thing is that usually you don't send one job and wait for the results and do the next, but you want to run many jobs. All of them parallel and bigger or smaller, but for parameter study, you send off 10 or 100, or in Adina's case, 50,000 or something like this. And this already brings us to the first and most crucial conflict that this will cause, and as you might be aware or not stumbled across it yet, a Git repository doesn't like it, that the local clone, doesn't like it if you have concurrent commands, Git commands that you run on it. Actually, this is forbidden. This leads to race conditions, or this is another word for undefined behavior. This is bad. Not good, must be avoided. But now this job scheduler, if there are enough resources and you have a couple of jobs from the same data repository, it might run it at the same time. You don't have control, you don't want to control. And this is, so you need to avoid this one. If this happens by accident, then you cannot tell what happens, probably garbage in your repository. So this is a really critical thing which we need to solve if we want to bring the Datalad run to HPC. There is also one inefficiency, and now you may say, I don't care, but actually for big jobs, the HPC centers will care and they will be mad at you if you have sequential commands, at least for minutes or more, inside your big parallel job, because then one CPU core will run your git command or the git nx-get or whatever, and the other 9,999 cannot do anything, and that's inefficient. They will kick you out if you do this a lot for big jobs. And then finally, maybe a question, or you can talk about it, but this reproducibility in a completely machine automatic way. If you need to go to your job script and replace this datalad run something with datalad rerun commit hash in a manual way to reproduce it, then it's not a fully machine actionable reproducibility anymore, because you change the thing manually. And so the Slurm job script should be fixed, should not need to change to reproduce it. So how could we do it? Oh no, one step back. Of course, how did people solve it or work around it so far? And this is actually Adina's and colleagues' work, which is at least the biggest case that I am aware of. Really the best possible way that you can do to circumvent this is to have one separate clone of your data repository per job. And you can do it, and then every single one is sure only one job will run at it, to git, check out, whatever, and it will work. But this, of course, causes a lot of redundancy. And it really, in this case, this fairly big data set, it was a couple of 10,000 jobs. And it will work, and I know you had to play it safe in some cases, but for this parallel file system, this is a big burden. Also in terms of not the volume of data, but the number of really small files. They don't like it, or they get really slow. That's why maybe this one would not scale any further. And I really would like to propose a different solution. And this is what we propose. Basically doing the git or datalad steps outside of the job, not inside this slurm job script. And we said there should be datalad slurm-schedule command that you run, and this will basically send the job to the slurm scheduler. And you can do so for many jobs in the same data repository. Then at some point you don't have any control that those jobs will run, and later on you come back with this Datalad Slurm-finish command, and this will look at one job or all the jobs that have been finished since then, and do all the Datalad save or under the hood git commit steps for you, and those will be one after the other sequentially again, and that's why it's safe to do them in the same clone of your repository. And then later, if you want to reproduce something, there's a slurm-reschedule thing, and this also needs to be finished with this slurm-finish command afterwards again, and then things work, and as you see on the right, you can schedule many jobs at the same time. You don't care when they actually run. You come back, everything goes to your repository in the Git log, and you're happy. A few more details that I'd like to touch briefly. When you think a little bit, maybe 1 minute more, then you have a chance in the middle of my talk, but one thing that could happen, of course, one job is overwriting the output of the other job. This is something which this slurm scheduler itself will not prevent. Here, we don't want to have something like this. Must not happen, basically. And that's why we say, other than for Datalad run, we say the outputs always need to be declared on the Datalad command line. And then internally, it makes sure that those output files or exclusive subdirectories per job are not reused by another job which is also in flight. If it finds something like this, it says, no, I will not schedule this job for you. And we do it with the SQLite database that's local to your local clone. And there we track all the jobs that are underway. And yeah, this works nicely and it's good enough. Then I said, yeah, rescheduled jobs also need this finishing in the end, of course. And then there's also the case where we need to say, what are we doing if a job failed, which can happen. And then the user can basically decide, oh, I still want those results in my Git history, or I don't want, and you do either of those. And also we produce some extra files. One is the job output. This is basically the standard out from your commands. And the other one is all the environment variables which tell you how your job ran as metadata in case you need them later on. Finally, there's a thing called array jobs where you send off many jobs of the same kind, and we also support it just like this. Yeah, so this is the way it works. And after this, we said we need a little bit of evaluation also how this behaves on a parallel file system. And they are really special because they are big and fast and everything. But for some things, they are actually slower or more sensitive than the SSD in your laptop. So you need to take care, and you will see something like this. The first thing, so we played it up to 10,000 jobs. This is basically much more than you would do. You would jump to array jobs before you get so many jobs, I guess. And one thing you can see here, that this is pretty noisy. So some jobs take really long, like 10 seconds or 11. But this is a usual thing from the Slurm job scheduler. Sometimes this is slow because too many people are talking to it, whatever. Down here, you see the rolling average. So this is like the average, but it does not change the sum of the time. And here you can tell it's like a fraction of a second that you pay extra during the Slurm schedule. And I would say this is just fine as the price that you pay for the added functionality. And then we look at the Datalad Slurm finish, so afterwards. And we see some of them behave nicely. Down here we have the zoomed y-axis. But the green and the orange one go through the roof here, and then suddenly they take more than 10 seconds, or it's growing and growing, 20 seconds per git commit. And this is too much, and also interesting why this happens. And this is of course not good. So we have one more special feature that we added down here. This is the alternative directory flag where we introduce, where we say if you have a local local file system like the /temp or whatever, where you can clone your Git repository, clone it there. And then, since all of the output and input files were specified in the Datalad command line, we can say, what's needed for the job? Only those we copy to the parallel file system. There they can run, and whichever node where they run can access the data. And in the end, in the Datalad slurm-finish, we just copy the results back. And you might say for big amounts of data, this will be more overhead than it saves, and that's correct. But for regular jobs, this is a solution. And you can see here for the uncritical schedule step in the beginning, it basically doesn't change. It's still fast, fraction of a second. And here you still see green and orange growing, but here those additional lines, they are behaving well. It's not going through the roof, so this is the one solution to the problem. And you can have, in the end, you can have repositories where you have like more than 50,000 files in it. Actually, this is the point where this starts, is the number of files in the repository, regardless if small files or big files. I have more benchmarks running. In fact, this is a problem which also happens on your local laptop, but the effect is much smaller, so you almost don't notice it. But I said the special behavior of the big parallel file systems make this problem much more apparent, and that's why we need this extra solution just in case. And this extra solution you only need once you went beyond the step where it appears. Before that, you just don't care, you work like normal. So you don't need to start with this in the beginning. Only when it's needed, you switch to the alternative directory thing. Yeah, for future work, we want to look at more parallel file system. We want to look at also bigger files where probably the balance between this problem and copying big files is different. And also we want to look more closely on the Git worktree, which could also be Git repository on a local file system, whatever, and then the separate worktree sitting on the parallel file system. And I guess there will be cases where the Git worktree way is better and our alternative directory is better in other situations. And we need to find out a little bit more. One special thing, just to mention here, we can do the results of all the jobs in separate branches, and we can also do the nice octopus merge that Michael pointed me to, and which I like as well, so this is built in. And yeah, with this, I'm at the end of this short tour, how the tool that all of you know for a long time would work or should work in a little bit different setting, which is also important and also important to me in my background, of course. So we have a solution. This is for the slurm scheduler. I think it's easy enough with the same principle to bring it to these 2 or 3 alternatives that are still around. We don't have conflicts anymore between jobs that may run at the same time on the same clone of your repository. We did a fairly large evaluation, which should be representative for also bigger computing projects where you might want to go to actually a high-performance computer. and also the stress for the parallel file system. We have something to reduce this. Future work, I mentioned a little bit already. So this break-even point, when the number of files become critical, we want to understand more different HPC file systems. And then as a separate thing, yeah, I want to use this one as a tool to make S3 storage protocol more used or better used inside those HPC clusters, not outside, but really inside. This could be a big advantage. And yeah, then maybe together with some of you, if you feel like, please talk to me. I would like to go out there to some of the usual HPC conferences and talk about this a little bit more. So don't introduce them to the Slurm thing, but hey, here is a nice way to have the Git tool that you all know, use it for data, really big data sets, and then make your research reproducible and use this tool. And here is how you can do it. I'm planning to go at the ISC conference, which is always in Germany. And if some of you feel like, oh, I would like to join there, I would be happy to. With this, I would like to say thank you. And of course, I'm looking forward to the questions after the next talk. Thank you.